What I was really wanting to discuss today, I think comes out of maybe there's sort of three motivations that I want to discuss for this angle on science education that might obviously is something that we're much more, I think, aware of for the reasons that Stavros said, but I think it goes back to a few different elements. First is the fact that it's some good news that science has been advancing so quickly in recent years, creating all sorts of new topics and subfields that have the potential to change our lives. But it comes along with this problem that now there are too many topics to teach that could be as important to learn as physics and chemistry and biology. And it's clearly more than any single school education could cover. Now, it is true that today there's a great access to online material, and it's possible to learn many of these things and many facts and numbers in by just Googling and just looking for YouTube videos. So there is a possibility of being able to approach this plethora of new ideas that science is offering us. But the problem is that it does come along with a real sense of confusion, I think, for people. It's not clear how the material should be used, what's important, and in particular, what should be believed. I think everybody feels much more vulnerable to fads and conspiracy theories, and of course, just plain lying. And it's had a very dramatic effect, of course, of, I think, leading this kind of confusion, leading to a real gridlock in being able to address any issues, as one side just disagrees with the other side. For a long time, I was very embarrassed about speaking about all this from the United States, since I felt that we're in particularly bad shape with respect to this. But the more I talk to my friends in other countries, the more it's sounding to me like everybody is feeling this concern. I think we're all aware of it now in Europe as well. In recent years, obviously, this kind of polarization and gridlock has hurt us badly during the pandemic. That it was hard for people to recognize what was good information, what was bad. You saw crazy concepts being put forward and not dealt with the way that we would have expected a modern society to be able to deal with them. And so in some sense, I'd say pandemics are a great example where these crises are not a crisis of scientific knowledge. They're really a crisis of public decision-making in the face of these highly polarized fears and uncertainties concerning facts. So it's obvious that this is not going to be the last of these kinds of problems. We already see that the same kinds of issues come up with respect to climate change and poverty and biodiversity, nuclear weapons. So this is something that we really have to face as together. It's perhaps, in some sense, the biggest challenge of our times. I think that if we're able to find ways to talk together and work together, I think I would personally be quite optimistic that we can handle all of those difficult challenges. But if we can't, it's very scary. Now, the good news, I think, is that today we do have a possible piece of this puzzle available to us in teaching the methodologies of science, because those have made it possible over the centuries to make real dramatic progress. And I think some of the same techniques are highly relevant to these group thinking problems in this current world. And of course, this is perhaps the piece of the puzzle that's been the least well used over the years. And so what I would like to do is take advantage of the fact that science for generations has had to face the question of how do we understand what really is real out there and what is it that we imagine. And you can almost describe this as a parallel echo that the credibility on the web today that we're trying to understand has real similarities to the problems of credibility of our picture of scientific reality. And examples of this that both have a tendency for people to try to use famous authorities as their way of establishing what to believe, and try to use what indications of popularity are out there as an alternative. And it's not that, as I say here, it's not that those are always wrong, but you really don't want Aristotle to be your last word of physics, and you don't want to be taking medical treatment based on some current fashionable rumor. So over time, science has dealt with this problem by teaching us a methodology that's been developed for centuries, but even still is being developed today. We still see updates every few years. And this methodology, this methodological approach is, I think, more of a combination of many tricks of the trade, many elements, rather than what we were, as some of us as children were taught as the scientific method, which I think is a very limited piece of all of these different tricks of the trade that we actually use. So what ties those together, I think, have some common themes. First is this very important lesson that I think we learn as scientists, that we are extremely good at fooling ourselves. And so we've had to keep learning, and we look for all the time new ways in which we're fooling ourselves, and then try to develop techniques to guide us so that we don't keep fooling ourselves that way in the future. And then many of these also are the tools and scaffolding that we need to deal with playing to our mental strengths and our physical capabilities, and avoiding our weaknesses. So those are two of the themes that we put together, I think, in this story. Now, when you ask what do these tools look like, this is something that I was trying to figure out. Now it's about 10 years ago, when I asked, can we recognize what these techniques are that we've been learning basically by osmosis as scientists going through graduate school and postdocs and teaching, and could we articulate them and then to teach them? And so I had asked to pull together a group of people to explore this. This is, I found the professors in other fields I felt were relevant to this: a social psychology professor, of public policy, a philosophy professor, and I also put a note up looking for graduate students, postdocs from the sciences, and I think the sign said something like, "Are you troubled watching our society make decisions? Come help develop a course. Come help save the world." And about 20 or 30 people started meeting every week. At the end of the week, we would meet at the end of a Friday, and we would go for hours trying to think of what would be a collection of ideas that would actually be important to explain and to teach in a much more organized way. And it led to a course at Berkeley that we called Sense and Sensibility in Science. And we've been teaching it now for basically most of these 10 years, always with 3 faculty members, one from natural science, one from social science, one from humanities. And over the years, as you can see, the faces have changed, and different people have played the roles. But it's been a very exciting and interesting experience to teach, and that's what I'll be telling you about. And now it's actually also starting to be taught in other universities as well. So it's something that we're starting to see spread. And the story that we ended up with consisted of some 23, 24 concepts that we thought could be roughly grouped into these topic areas. And I'll just describe a little bit of that to you today, just so you get a flavor for what we're talking about. Let me just reorganize this a little bit to show you that we were thinking of it a little bit as the upper left are these sort of cautionary elements of science. On the upper right is the drivers of science, and then these lead to the elements that have to do with human thinking at the bottom. And so I'll just walk through just a few just to give you a sense of what these are. Beginning with the cautionary elements, let me start the upper left, the underpinnings of science. We often, some of these are actually really philosophical points. They begin with something that I think we almost now take for granted, but we apparently shouldn't. And as we've seen in the last few years, that we live, that in some sense we've made progress in the world by a belief that there is some actual shared reality out there, that there's something there that we're trying to understand. It's not just everybody makes up their own picture of reality and they go to their own corner and believe what they want to believe, but we come together and we try to explore where the differences are and what it is that we need to understand together in order to recognize what's really happening out there. And we sometimes use the metaphor that you don't want to stub your toe on reality just because you think it's different than it really is. This leads also to a bit of a discussion of some of this metaphor of the pyramid versus the raft of knowledge, and the idea that is there that the pyramid of knowledge suggests that there's some fundamental foundations, and if we ever shake those foundations, the whole thing falls apart. But that's not really, I think, the way we actually tend to do this understanding of that reality out there, because we don't have that a fixed, rigid understanding. We know that it's a objective reality, but we don't necessarily get to see it. And so what we end up with is more of a raft of knowledge, where we have many different elements of a story that we have fit together that we think floats, that makes sense. But if we end up challenging any one of the sticks in the raft, it could be that we come to the conclusion that it's waterlogged and we have to throw it out and we put another one in. And it doesn't shake the whole process because we still have a floating raft, unlike in a pyramid that falls apart. An example you might describe is that if you find that Newtonian gravity it has some parts that it doesn't quite cover, and we had to switch to Einsteinian gravity. The whole picture of our understanding of gravity doesn't fall apart. We don't ground all airplanes until we figure it out. We still have basically a picture of the world that is roughly working at any given moment, but we are willing to give up the idea that Newtonian gravity is a log at the end of the day that's has to be kept. There's a lot of the underpinnings also include the topics of causal reasoning. I think many people are familiar with all the discussions about correlation versus causation, but that's a topic that's becoming particularly important in a modern world of modern data-rich world, where there's so much data that people are looking at and so many plausible relationships that you can read about, and you need ways to be able to help distinguish, what's just a correlation that you can see from things that have actual causal connections. We sometimes teach, we do teach, things like randomized control trial techniques as sort of a gold standard of identifying a causal connection. And of course, that's become very visible in the medical world. But it's also important to teach that there are other ways in which we establish causation when you cannot do a randomized controlled trial. And so there are parts of the story that we teach about that. Obviously, a field like mine in science wouldn't work if you do cosmology. You can't really do very much in the way of randomized controlled trials, and yet we still can make progress. And the same thing can be said for many aspects of our social and political world, where you can't always do an experiment. Sometimes you have to come up with other ways to figure out what causes what. Okay, so another aspect of the cautionary elements of science is this aspect of probabilistic thinking. And that seems to be a key tool that we all use in the sciences all the time, but that doesn't seem that the public always recognizes. Sometimes we think of this as the underpinnings of statistics, but what's really important here is, I think, for everybody to understand why we use statistics, not necessarily any of the recipes of statistics. They're much less important than recognizing the reasons that we will need it. So first is just the idea that we are constantly in a position of trying to pull out some signal that tells us about the reality of the world out there from noisy situations. But when you do that, it turns out you start to see that humans are really, really good at seeing patterns in noise. But the problem is that they're so good at it that they tend to see patterns that are false, that are just spurious, even in random noise. And that distinction between being able to recognize when are you seeing something that's a true signal and where you're seeing something that looks very meaningful, but like a series of heads when you're flipping a coin, but happens with random numbers, not that don't tell you anything meaningful. And that's actually a very important skill for people to recognize even just what the problem is, so they know why they should go talk to a statistician or why they should learn some statistical tests. I think one of the things that many scientists have learned just through their own experience of doing research is that they've fooled themselves at times into thinking that they had something significant, and then they had to learn how often that will happen for statistical, purely statistical randomness. Maybe even more important is the recognition that almost all of the statements that we make and almost all of the things that we think we understand about the world are tentative in some sense, that they have some probability associated with them. So some of them we can be very certain of, you bet your life on them, but those are still only 99.999999% confidence. Whereas, most things, or many things in the world, we have much lower confidence in. And just being aware of that and having some sense of what those confidence levels are is already an important tool, because it makes it psychologically easier for us scientists, and we think everybody, to be open to being wrong. That you don't want to have to, stick to your guns to be a respected person. That you sometimes what you're respected for is the fact that you recognize how strongly you know something, or how tentative something is known. And if you say something is 90% confident in something, then 1 out of 10 times you say that, you expect to have to change your mind. You expect to be wrong. And and I think that's very important flexibility in thinking that comes along with probabilistic thinking. So for every one of these concepts that we've been teaching in this course, we usually spend a whole day on them, and or a whole class on it. And each concept, we try to come up with ways for the students to experience the problem. So just as an example of that, I was going to describe the game that we play for this particular concept, which is that we have the students have a bit of a discussion together on the question of just some arbitrary question. In this case, it's, has the increased use of standardized testing in the US elementary schools improved the quality of education or made it worse? But during that discussion, we have the students state their likelihood from 0 to 100 after every proposition that they state that it's of whether they think it's correct. And then they sort of remind each other if they get it wrong, if they forget to give a number. So so you get statements like, someone might say, most teachers have now begun to teach what they think will be on the tests rather than what they think is the most important material to teach 82. And that's my percentage of confidence in that statement. What's interesting is that when you ask the students afterwards, they say that they find in the course of doing that game, that exercise, they find themselves realizing that they often don't have a strong confidence in statements that they're making as they might have thought they were. And in fact, they become a little bit more open to the possibility that, well, if I think this is true 82%, what about the other 18%? Maybe we should consider what would the world be like if that turns out to be correct. And I think that's a very important trick of the trade of science that we've all taken advantage of.